Hope you are able to see my screen. Yes, can you see my screen?
Yes, sir.
Yes, sir.
Very good. So after my talk, I will share the recording link for the video of this lecture by email. Okay. Let me first begin by just sharing another screen. So just 1 second, please. I want to talk about this course outline. Maybe before I do that, I should just say, because you are all first year students, you are meeting me for the first time, I should say a few words about myself. So my name is Parameswaran Sankaran, Paramesh for short. I did my PhD in University of Calgary in Canada. It's a very, very cold place. So it was real, I mean, a terrible shock for me when I landed there. When I left, I made the mistake of joining there in winter semester. So before that, I had not been out of Chennai. So when I left Chennai, it was plus 25 degrees, and when I reached Calgary, it was minus 25. Anyway, so those days are all over. And after my PhD, I was a postdoc, and then I came back to Chennai. I joined Institute of Mathematical Sciences as a postdoc. Then when CMI started, that was in 1989. I was there from day one for about 11 years. Then in the year 2000, again, I went back to IMSC, Institute of Mathematical Sciences, and I was there till 2019. And in 2019, I came back to CMI once again. And for much of my academic career, I had not taught undergraduate program. So from 2019, I've been teaching undergraduates. Of course, in Canada, while I was there, I had taught undergraduate program, in the undergraduate program, and in fact, even taught discrete mathematics, which included probability theory also a bit. So, okay, so these are a few words about me, and yeah, and I want to talk about this probability theory course. Yeah, so the course outline and everything is given in the CMI web page on teaching. So if you look at, you probably know where to find that information. Nevertheless, I want to share some specific information about this course. So I will share some other screen. Just a minute. I will just 1 second. Stop share. And just 1 second. So, okay. All right. So now I share a different screen. I think you will get this also soon. Are you able to see this? Maybe I make it full screen. Can you see my screen?
Yes, sir. Yes, sir.
Yes, sir.
Yeah. So, okay, the maybe the font size is very small, so you don't read it properly. I'm not going to waste your time reading the syllabus. It's exactly as given in the CMI website. So now the textbook that I intend to use is Grimmett and Stilsaker, Probability and Random Processes, Oxford Science Publications. A legal copy is available for free download. So you search for it in Google and you will find it. Okay, and we will be following this book. Of course, this book is voluminous, and we will only cover the relevant portion from this book. Okay, it's impossible to do the entire book. I mean, that would be spread over several courses. So whatever is there in the syllabus, that's already contained in this book, and I will follow that. Okay, and also I have given some reference. It's a very classic filler, an introduction to probability theory and its applications. If you search the web, you may be able to find a copy of this also. And now the next important thing is assessment. So there is this continuous assessment and final end semester exam. For assignments and quizzes, I have assigned a weightage of 25 marks. Okay, so roughly, I mean, it could be 25, it could be 30. For mid-semester exam, final was an add up to that. So I may as well, sorry, I have to change this slightly. So so let us say make it 35. Yeah, so assignments and quizzes 35 marks, and mid semester 15 marks, and final exam 50 marks. Okay, so your overall grade will be for, I mean, based on the total mark you obtain for 100 marks. Okay, out of 100, whatever be the thing, accordingly the grade will be assigned. So this is what I want to point out. So now I think this file can be closed. So just let me close this and we go back. Stop share. Okay, so now I go back and share the other screen. Where is that? Okay, sorry, I should just pull this out. So just once again I had to share. Are you able to see the screen now or no?
Yes, sir, it's visible.
Probability theory, this screen where I have written probability theory and put the date, is that visible?
Yes, sir.
Okay. One other thing I should tell you, I basically I am a topologist. I do group theory and so representation theory and topology and so on. Probability theory is really not something I do often. I mean, it's not an area in which I do any research, but I like this. So, okay. Let us get started with. You have all studied a bit of probability theory in 12th standard. So typically, okay, you have some sample space and possible outcomes are written down. So you perform a random experiment. Maybe it is a coin toss experiment. You know the outcomes, head or tail, and then okay, so you have to be told whether the coin is biased or unbiased. If it is unbiased, then we know probability of head is half, probability of tail is half, and then you do this, make calculation of whatever required probability that you want to calculate. And maybe you have seen also some further type of thing where you roll a die or maybe a pair of dice and then look at the outcome and so that gives you your sample space and some subset of that. If you are given, you can find out what is the probability of that event occurring. But you see, the thing is, there are, to begin with, how do you assign probabilities? So suppose I toss a coin, there is no reason to believe that my coin is unbiased. So you can just say, okay, half half. But but that's to begin with is an assumption. Yes. So classically, the way it was determined was you toss a coin some 10,000 times and then observe, and maybe if it turns out to be some 5008 times head and then remaining times tail, so you probably believe that the probability of head is half and so on. Otherwise, maybe it is bias and then you sort of proportionately assign your probability. Yeah, so basically the classical definition of assigning probability for so-called elementary events is based on repeating an experiment many times and observing the frequency with which a particular elementary event occurs, and then the further calculations can be made based on that. Okay. But there are practical difficulties of carrying out this type of thing. For example, you may want to assign probability that it will rain tomorrow in Chennai. So no question of performing experiments hundreds of times or anything and then observing and so on. So you know, so uh, uh, there are a lot of philosophical issues in assigning probabilities, in making very precise, the intuitive understanding of uh, what should be probability of an event, what is an event, and so on and so forth. After a lot of, um, proposals, it has now been sort of mathematically very rigorously formulated what should be a probability space and what is probability and so on and so forth. So that is where we begin. Okay. So first of all, okay, we um, assume we are all familiar with what a set is. This is already, we have to begin somewhere. So we are not going, let us not get into mathematical difficulties in formulating axioms and so on and so forth. So let's just start with the understanding that we all understand what a set is and what it means for an element to belong to a set and so on. Okay. So let omega be a set and let f be a collection of subsets of omega. Typically, if omega is a finite set, script f will consist of all possible subsets of omega. And possibly also, if omega is a countable set, you may take f to be all possible subsets of omega, no problem. But in general, you may have to restrict the collection of this set, this collection of subsets f. Okay. So you will see situations where that is more or less required. But we will assume that f is what is called a sigma algebra. So I'll have to say something about this f. We assume that the following properties hold. So empty set must be in F, and and also the whole space omega is also in F, and then so if A1, AN are in F, then union. A is equal to union of all these AK, K bigger than or equal to 1. So it's closed under countable union. So that's what the second one means. And the third one, if A is in F, then A complement, which means, of course, omega minus A is also in F. So if F satisfies, so such a family of subsets is called a sigma ring, or some people say sigma algebra, sigma ring. Okay. Later on we will put one other condition, but at the moment it is not relevant. Okay. So yeah, so you must what is going on here? You must think of omega as possible outcomes of an experiment, and F is a collection to which whose members will be called events, and we are going to assign this notion of probability to events. So I'm going to define for you a probability space. Probability space. So is a triple. So omega, F, and P, where P is from F to 0, 1. So this means closed interval 0, 1, real numbers, okay, such that number 1, probability of empty set is 0, and probability of the whole space omega is 1. Number 2, probability of so union union over all these K, AK. Yeah, okay, let me write that here. Suppose that. So this condition is what is called countable additivity. If A1 blah 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 AN or pairwise disjoint subset, sorry, okay, I use an abbreviation. Better not use it. Disjoint subsets, disjoint sets in F. So each one of them belongs to F. Then I can talk about probability of the union of AK, K bigger than or equal to 1. That's equal to sum of K is equal to 1 to infinity probability of AK. Okay. So
Can the question? Sir, can I ask a question?
Yeah, sure.
You're calling this countable additivity. So this
Yeah.
is countably infinite additivity.
Yeah, this is a countable collection. A1, A2, blah, 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 AN. I'm not saying each AI is countable or anything like that. I'm just saying, so as opposed to finite additivity. Finite additivity means that probability of A union B is probability of A plus probability of B if A and B are disjoint. So that is finite additivity, just only two sets. And once you have it for two sets, you can prove it for any finite number. So you can state finite additivity as suppose A1, A2, blah, 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 AN or pairwise disjoint, only a finite collection. Then probability of their union is sum of the probabilities of each one of these AJ. Okay. And here we are allowing for each AI to be countable. So in particular, of course, this will be a convergent series, and it converges to some number, and that number is exactly this probability. Yeah, and then what else is there? I suppose that's it. Only these. Okay. So so that's it. And now you can establish some properties. I will work out some problems, but at the moment, just let us get some formalities over with. So countable countable. So that's it. Okay. Additivity implies finite additivity. Finite additivity. So that's clear, right? If A1, AN or in F are pairwise disjoint, disjoint, then probability of A1 union AN is equal to sum of the probabilities AK, K equals 1 to N. So, okay. And in fact, it's enough to state it for N equals 2 and then follows by induction for any N, finite N, no problem. But from finite, you can never go to countable additivity. It only works one way. Yeah. So that's something to remember. Why?
Sir,
Yes.
so
Yes.
are these subsets itself needs to be countable or just
No. Yeah, that's exactly what I said. AIs need not be countable sets. They could be like an interval, for example. A1 could be, all rational numbers, for example. That's okay, that's countable. But A1 could be all real numbers between 0 and 1, for example. It could be of that nature. Okay. So nothing is stated about these AIs themselves being either finite or countable or anything. Nothing is assumed about the cardinality of omega. Omega can be very huge. And yeah, so nothing is assumed. I mean, the countability here, countable additivity, this one refers to the number of sets that you have here. You see A1, A2, A3, blah, blah, blah. It's a countable collection. You could have an uncountable collection, but then it doesn't make sense to write here. Uncountable collection of disjoint sets is very much possible, but it doesn't make sense to write a summation over an uncountable set of possible real numbers. So that makes no sense. Okay, so that is exactly what we mean. So countable there refers to number of sets being countable. Each set may or may not be countable. We don't care. That is irrelevant, totally irrelevant for us. Of course, the case that you are most familiar with, omega itself will be a finite set. And therefore, F will be, if omega has n number of elements, F will have at most 2 power n elements. And each member of F itself will be a subset of a Omega therefore a finite set. So that's a very special, extremely special case. Okay. All right. So, but before we proceed, we need to establish some properties so we can use them to do problems. So let me just state those things. Lemma. So probability of, so it's understood that when I write A, probability of A and so on, they are members of F, script F. Okay. So this is, I will write only briefly 1 minus probability of A. So for all A in omega in F. Okay. So this is number 1. I will prove some of them, but not all. Okay. If B contains A, and when I write like this, I do not exclude the possibility that B equals A. Okay. So some people write here another underline, but I'm not used to writing that. If B contains A, then probability of B is bigger than or equal to probability of A. These are all fairly obvious statements. Probability of A union B is something you are all familiar with, additive formula or something. Probability of A plus probability of B minus probability of A intersection B. And yeah, so this has a more generally, so number 4, more generally, if A1 blah 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 AN or in F, we are not assuming they are pairwise disjoint. So now this is arbitrary, then probability of A1 union blah 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 union AN, this is equal to summation probability of AJ AI minus summation, so I is equal to 1 up to k, 1 up to n. So here I less than j, probability of AI intersection AJ, and then plus summation probability of AI intersection AJ intersection AK, and so on. So here I less than j less than k. In other words, all are distinct, and you may as well arrange them in increasing order of the indices, and then plus minus 1 power n minus 1 probability of intersection of all of them. And this can be proved inductively from 3. 4 follows by induction from item 3. Okay, so then what else is there? Yes, number 5. I have this number 5. Suppose that A1 is contained in A2, contained in blah blah blah, contained in AN, are all in F. So you see, you cannot talk about probability of something which is not in F. So you need to keep saying this. Okay. Then, so writing A is equal to union of all these ANs. We have probability of A is equal to limit n goes to infinity probability of AK, AN. Okay. That's something to be expected. So, and similarly for intersection. Similarly, if A1 contains A2, contains A3, and so on, contains AN. So this is a nested family, decreasing family of sets. And AJ, AN is in F, then probability of the intersection of all these guys, an. This is equal to limit n going to infinity, probability of an. Okay, that is it. I think I should prove at least some of them. I will prove some very basic ones. So not everything. Okay. Proof. Let us prove the first one. So probability of a complement. Yeah. So we want to find that. Okay. So write. Write omega is equal to A union A complement. Okay. Then A and A complement are disjoint. So I know already 1 is equal to probability of omega, and that's equal to probability of A plus probability of A complement, because A and A complement are disjoint. So this implies that probability of A complement is equal to 1 minus probability of A. Fairly simple. Okay, now I must take the next page. Oh, okay. So number 2, I don't recall what is number 2. Let's see. Yeah. If B contains fairly, this is also fairly easy. So write B is equal to A. B contains A. So I can write it as A union B intersection A complement.
Hello,
Okay.
sir.
Yes.
Sir, we define the family F corresponding to a given set omega, right?
Yeah.
So in the previous problem, I mean, we considered omega to be A union A complement, but A and A complement were given to be members of a particular family. And how do we actually know that that family is the corresponding, I mean, the power set of this given, I mean, this set that we consider to be omega?
Okay. See, I'll tell you what is happening. So here I didn't write the full statement. Yeah, I wrote here for all A in F, right? So A comes from F, correct? If A is
Yes,
in F,
sir.
A complement is also in F.
Yes, sir.
Then that's all you need. Therefore, you can make sense of probability of A complement. Yes. So
Yes, sir.
now omega can always be written as A union A complement.
Oh, okay, sir. Yes, sir.
Omega is always
Yes, sir.
expressible as A union A complement.
Yes,
I
sir.
already
Yes.
know A is in F and A complement is also therefore in F. Yeah.
Yes, sir.
So
Yes.
see, in all these things, I'm not, just a second, please. So I'm not changing my F from problem to problem. Some axiomatics is already written up. Okay. So this F, the main thing that you probably haven't come across is this fuss about F. F need not be the whole subset, all possible subsets of omega. Certain subsets are singled out and they are called events. In fact, I have not even given any names for these things, but I should. Okay, so that's the only thing. But once you are told, okay, I have a probability space omega, probability space, that means I'm given all these data. Okay, and for that I'm just proving some properties which follow from the axioms. That's it.
Okay, sir. I get that.
Yeah. So now I know that B is in F, and I write B as A union B intersection A complement. Notice that since A is in F, A complement is also there, and B intersection A complement is also in F. Why so? See, one has to, so this Yeah, let me make a comment about that. That's again something, some property. See here, I didn't say anything about intersection. Okay. See, I made a statement about union, but why are things close under intersection? That would follow from here. Okay. So if you are worried about that, I will make that as a aside comment. So here. Okay. So suppose, in fact, you can write here an. So an or in F, n bigger than or equal to 1, then intersection an is also in F. This was not an axiom stated for sigma ring, okay? But it follows because the moment an are in here, then I can say an complement or in F, right? So I take union of an complements. That will also be in F. Okay. And now look at omega minus, this implies omega minus union of an complement. So in other words, I'm looking at the complement of an complement. Okay. So this is equal to, you understand? So this is just De Morgan's law. So union of, so this is equal to, this is also, so okay, let me write here. This implies that union is, yeah, this complement is in F. But this is same thing as intersection of ANs is in F. Is that clear? So countable intersection is itself there. So finite intersection is not a problem. So you see, we write the axiom system in a sort of very redundant, in a very, non-redundant fashion. Don't write all the implications also as part of the axiom. Okay, so that means that this one is very much in F. And now write probability of B is equal to, and these two are disjoint. So probability of A plus probability of B intersection A complement. And this, of course, this is greater than or equal to 0. So therefore, this is bigger than or equal to probability of A. That's what we wanted to prove. And so on. Next, what is the statement? 3 is now fairly easy and straightforward. 3. Okay. So probability of A union B. We want to write this. What is this? So A union B, I can write it as, how can I write it? Is equal to A union B complement, I suppose. B complement. No, sorry. A intersection.
Union B minus A.
Yeah. Union B. And these two are disjoint. Yeah. Okay. Yeah. So now these two are disjoint, so I can write this B of A union B. Probability of A union B is probability of A intersection B complement plus probability of B. Switched off. Please. Yeah, so I have written it like this, and now so one has to write down probability of B, A intersection B complement, probability of, so I can write A, probability of A as probability of A intersection with B union A intersection with B complement, and that's equal to probability of A intersection B plus probability of A intersection B complement. So you need to substitute for this, therefore probability of A intersection B complement is equal to probability of A minus probability of A intersection B, and you substitute that in here, okay? Therefore probability of A intersection A union B. This is now your familiar formula, probability of A plus probability of B minus probability of A intersection B. Okay. And from this, the other more general formula will follow, and I will not even comment about it. That's left as an exercise. And let me now prove 5 for you.
Sir, I actually have a question about 4, like the general version of like the. Sir, does it hold for like does it generalize for countable collections of subsets of?
No, that's not true. In fact, it's not true. Yeah. From finite additivity, the examples are difficult to give, but finite to countable, you just cannot pass to the same by any way. Simply not possible. That has to be I mean, okay, first of all, yeah. See, let me talk about that. This one, okay, suppose you assume this for only finitely many sets, you will not be able to say anything about countable additivity. That's what I was saying here. Countable additivity implies finite additivity. But
Sir, I didn't necessarily mean if you can like you can deduce the count, like the formula for
okay.
like countable
So here
from this.
this itself, we want to know whether you can extend it to you see, the signs keep alternating. There may be some problems with that, but I suppose
Can we
I suppose that that you in fact, next theorem, next property tells you that it is whatever you expect will be correct. You see, the thing is, you can assume that it is nested. In fact, that's exactly what we did here also. So you write A union B, I mean A1. So sorry. So here you want to write this for the union, right? A1 union A2 union AN, and you want to generalize it to also infinitely many sets.
Yes, sir. Yeah, like
In
the countable
sense,
union.
in
Yeah.
some sense, that's exactly what is going on here. See, suppose you want to prove it by induction. How will you do it? You will write A1 union A2 union AN minus 1 within bracket, and then union AN. Okay, and now what you can do is well, I mean, yeah, you
Sir, do you mean that like that final A, like from property 5, the final A is actually constructed by like taking the union with AN.
Absolutely.
Keeping on doing that.
If you are given a countable collection, what I can do is say, suppose my collection is B1, B2, B3, etc. Then I will take A1 to be B1, and then A2 to be B1 union B2, and so on. AN to be B1 union B2 union blah 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 BN. Okay, and now what you have is formula for each probability of each AN. Okay, and now you want to know the formula for probability of A. And this is what I mean by saying you can use this, but directly writing that here will be problematic because, well, even so, I think one can give some justification, but this is the right way to say it also. So in some sense, arbitrary, I mean, countable union is covered here. Although you don't see it. See, do you understand what I said? So
Yes, sir. I think I got what you meant. You meant that it exists, like that in countable union, right? There does exist like a probability that you can assign to it, but it's not trivial to just take the above formula
Yes.
and put it for infinity.
Yes, yes.
Okay, thank you, sir.
Mhm. So
So it
now,
would also be rearrangement problems probably if we do countable instead of just finite.
yeah. So suppose that. So now, okay. Now we are going to write like this. Right. Let me take blue color. Right. So you have this A1, no? A1. So we have AN. See, they are all nested, no? So I can write like this. This is equal to A1 union A2 intersection A1 complement, and then union A3 intersection A2 complement, and so on. Union AN. In fact, I want to be able to write AN itself like this. A itself. Okay. And then AN intersection with AN minus 1 complement, and then union, and so on. So you put like this. Okay. Now, because A1s are all nested, since A1 contained in A2 contained in blah, 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 AN contained in the above is X. So the above is an expression, expression of A as a disjoint union. So, disjoint union of members of F. Yeah. Members of F. Therefore, I can apply that countable additivity axiom. So probability of A is equal to sum over, okay, probability of, first of all, A1 alone I just single out because from then on, probability of A1 plus summation probability of AK intersection AK minus 1 complement, and here K is bigger than or equal to 2. Okay. And now, so you write this, okay, so yeah, so write this. So P of A1 plus intersection, so summation. I write only up to K, so 2 less than or equal to K less than or equal to N, probability of AK intersection with AK minus 1 complement. This is, you simplify this, there will be telescopic cancellation. Okay, so let me write this. So there's not much space. I try to squeeze it in. Summation probability of AK minus probability of AK minus 1, precisely because AK minus 1 is contained in AK. and here k equals 2 to n. All right, and this is so P1 will cancel with the first term here with the negative one. So I get probability of an. All right. Therefore, so let me show that last slide. That therefore, what do we get? Probability of A, which is equal to. So you see, you have an infinite sum limit. So I rewrite it because it was in the previous slide. So summation probability of AK intersection AK minus 1. Here k bigger than or equal to 2. This is equal to limit n going to infinity probability of A1 plus I write it only up to this. That's the meaning of writing that sum 2 to n probability of AK intersection with AK minus 1, which I have already calculated, and that is limit n going to infinity of probability of an. That's it. Okay, so I think, and the last property is similar. Is that clear to you? So you see, here well, I mean, you think about it, this step I didn't explain, but it's rather trivial. So that's another bracket here. Sorry, I had to squeeze that in. Okay. All right. So now, yeah.
So you have given summation P of AK intersection AK minus 1. So wouldn't it be
AK minus 1 complement? Sorry, I forgot to put that complement here. Here also, I was careful in the previous step, but when I copied it, I forgot the complement. Yeah. Is it clear now? Is it clear?
Yes, sir. Yes, sir.
Okay. Yeah, I want to work out some problems.
So will these notes be available later on after the class?
Will what be available?
These
oh
notes.
yeah, definitely. Of course, it will be available. So try and understand what I'm saying. These notes will definitely be sent to you today itself. Okay, I will. I haven't really fully learned how to use Moodle. Sooner or later, it will be up in Moodles. But for the time being, I will send it by email. Okay. Yeah. Let us work out some specific problems. Yeah. I'm not going to do very routine, simple-minded problems, which you probably have done in your 12th standard. So, examples. Yeah, the previous time I taught, I spent quite a bit of time doing elementary things, and in the process, I didn't have time to discuss one topic which I really wanted to discuss. But this time, hopefully, the time will be used in a more efficient manner. Okay, so here is a coin toss experiment. A fair coin. Yeah, okay, let me say the following thing. Although I made all this fuss about omega and f and so on, this is a way you have to learn it. But in specific problems, we don't need to spell out what your f is. Okay, script f, what your omega, those things will be clear from the context. And I'm not going to really formulate what your f is. Okay, so by the way, omega is called, I think it's called sample space, and F is said to be collection of events, and P is said to be the probability function, of course. So maybe I just say sample space. So that I write something here. Sample space. This is omega. This is collection of events. Of events. So usually it will be clear what these events
Excuse
are.
me, sir.
Yes. Yeah.
Sir, I wanted to ask this. We have defined the probability function explicitly to like the range as 0 to 100. We defined it. So is it the definition, or because what I am thinking is, say you have an event A, then because like omega is going to be A plus A complement, we can establish that A will have a probability between 0 and 1, since phi and omega are having like 0 and 1 respectively. So isn't it like implied with the other properties? Do we have to actually explicitly write that it has to be between between 0 and 1?
I had to say something, otherwise it would not be true. For example, so I already said that omega, probability of omega equals 1. Okay.
Yes, sir.
And then that additivity, from that it would follow. But I still have to say, why can't probability of A be minus 5 and probability of A complement equal to 6?
Because phi is 0, right? So
Phi may be 0.
Okay.
See, I have to specify the range. Without specifying the range, it's not possible to show something. It could so happen, I mean, see, what are we saying? You have a collection of functions f. If I don't say where, so let's go back. Okay. If this is, for all you know, some collection of sets, and I'm giving you values of this set only at 2 points, two of the members, empty set and the whole set. And suppose I didn't say it here, I just wrote real numbers. Okay. Okay. Then there is absolutely no reason to think that probability of A is going to be positive, or that probability of A is going to be less than 1.
So, but empty set is contained in A and A is contained in omega.
So what axiom
should
tells
be
you?
between
What
0 and
axiom
1.
tells you that probability? So this we proved this only by using all those conditions that were given. For example, in probability of A complement equal to 1 minus probability of A, we already used something. Probability of omega is 1. But okay, from this you don't know that probability of A complement is a non-negative number. Do you know that? That will depend on the value of probability of A. I mean, what prevents me, for example, let me say, suppose I take my set, my omega to be head and tail. Okay. And I assign probability empty set to be 0, probability of omega to be equal to 1. And I say probability of head is 5 and probability of tail is minus, let us say minus 6. Then which axiom will be violated? You tell me.
So yes, so it basically, if we have already specified it to be say F2R plus, then we'll be able to establish. But we'll have to specify that it is
Then
positive. Yes, sir, I get it.
yeah. So you have to say something. Yeah, that's right. Yeah. Yes. Okay. So definitely you have to say something. We just cannot. Yeah. Okay. Let's move on. Yeah, you cannot simply forget mentioning the range altogether. Okay. So a fair coin is tossed indefinitely or repeatedly. Okay. So show that a head appears eventually, sooner or later. And this next sum is also next subdivision. Show that any given finite sequence, so show that any given finite sequence of heads and tails. So you prescribe that finite sequence, heads and tails, appears eventually. Eventually meaning when you repeat this, keep on tossing, sooner or later you will find some finite string coinciding exactly with the pre-assigned string of heads and tails. Okay. And with probability 1, eventually, with probability 1. Okay. Isn't that surprising? Is that surprising or no? The last one, or is it counterintuitive?
Sir, could you please explain the second part once more?
Yeah. So let me say that. Suppose I just write randomly. So randomly I write H, some T, H, T, H, T, H, T, H. And I have written some string. So you keep on tossing your coin maybe a billion times. Sooner or later, you will see this string appearing somewhere. That's what it means. And eventually with probability 1. Is that surprising or no?
Actually, not. It's not that surprising. Sir.
Okay, very good.
Not that.
Yeah, well, we will see.
Does this probability 1 means like it will appear for sure?
It will appear eventually for sure. It doesn't say it will appear for sure. I mean, it doesn't say that if you toss it a billion times, it will appear. We don't know when it will appear. But you keep on tossing your coin any number of times repeatedly, and you just simply keep recording your observations, and you will see that sooner or later, this pattern appears.
Okay.
Okay, so let me prove the. Let's do this first one. Okay, let's do the first one. Okay.
Sir, aren't we first and second one like the different different versions of the same thing?
Pardon me, you are saying B, A is a different version of the same as B? Is that what you're saying? No, I didn't understand what you said. Couldn't hear properly what you said. Can I go on?
I think he said B is a different version of A.
Okay, sorry, sir, I got disconnected for a while. What I was asking is, aren't A and B like different versions of the same thing?
Yeah. Okay, maybe, if for a mathematician, perhaps it makes no difference, but you just tell a common man, probably the person will believe A and maybe view with suspicion statement B. Okay, but they are of the same kind. Mind you, there is a big difference between the two. You just want to have one head appearing, and probability of a head is just 1/2. Okay, so fair coin, therefore probability of head appearing is 1/2. Whereas here, this string, for it to appear once, will be, suppose I have written 15 letters, I don't know, I didn't count. So it will be 1 by 2 power 15. Even to appear once, in this, that 1 by 2 power 15 is a very small number. But then the thing is, you are indefinitely repeating this coin toss. So eventually it should appear. That's what we should expect. Okay, but it's somewhat surprising, at least on a first reading, why it should appear at all. I mean, why can't I just, flip the coin indefinitely and maybe I never get to see this pattern? Okay, so there is a qualitative difference. Here, probability of head is half and probability of tail is also half. Here, for this event to occur, well, it's not exactly probability, it's half. That's the only main, that's I think the main difference. But because of this word eventually, it really doesn't matter. Let us quickly finish off the proof because...
Sir, could you explain by a small example? I mean, what is the difference between appearing and appearing with probability 1? I mean, for an event to appear and...
Okay, see, so you can say, I mean, so you say, now, how to explain that? Yeah, when you conduct an experiment, okay, suppose you have tossed a coin, all right, you observe the outcome. It's either a head or tail if you toss it once. If you toss it 2 times, maybe you can list out 4 possible ways. Okay, so then you can talk about, all right, probability of HH is 1/4. You all know that, correct? Yeah.
Yes, sir.
Now you can, when you say it appears sooner or later, this is a meta-mathematical way of saying that eventually probability of head appearing, if you keep on tossing the coin, is 1. Okay, that's the... So this is not written in a mathematically very precise way. So quite often in probability theory, or let me not say probability theory, quite often when you have a real life problem, it is not formulated in precise mathematical terms. You have to find a model, okay, and then you have to interpret what your expectation is, what your conjecture is, what your guess is in mathematical terms. So this is written in a meta-mathematical language, the precise meaning of which is that if you keep on tossing the coin repeatedly, indefinitely, head will appear eventually with probability equal to 1. Okay, so that's the same thing that is written here in slightly more precise mathematical.
Okay, sir. Okay,
sir. For the second question,
yeah,
is that means that for every finite sequence, if we like toss and toss again and again, we'll find a subsequence of that sequence that will match with that finite sequence. Is that
absolutely? That is absolutely, that's what I mean. But one should be a bit careful. When you say subsequence, you can take second term and then the 10th term and then 23rd term and so on.
Substring, consecutive.
Substring, which is consecutive. Yeah. Yes, so I didn't count, like I said, maybe there are 15 letters I have written down here. You take a consecutive block of 15 things and that matches with this. That's what I mean. Okay.
Sir, I think PHP can help in proving the second part.
Pardon? What will help?
Pigeonhole principle, I think.
I don't know, but it's not. I don't think it is pigeonhole principle. But anyway, let me explain that first thing first. Okay, so what is the negation of this statement? The negation of this statement is that head never appears in A. the negation of this given statement is that H never appears. So let us compute the probability of that. Probability that in n tosses, so in n tosses, T occurs all the time equal to, this is 1 by 2 power n. Okay, so what is the probability that this happens for every n? And so that limit n going to infinity p of, well, t power n, let me write it as t n-fold, is equal to 0. So therefore, eventually, we don't know exactly at which stage, but therefore, eventually H appears. Okay, that's it. And for B, well, suppose that we are given a string, of length, k, consisting of heads and tails, consisting of H and T. And now, so consider, okay, so now what I'm going to say is the following. I have only 3 minutes, I'll say it quickly. You see, consider K tosses as a single experiment. So each experiment consists of just tossing K tosses. Okay, let us just call this string equal to S. Then probability of S is equal to 1 by 2 power K. You are given very specific string and you want that to happen, and this is it. And probability of S complement, this is equal to 2 power K minus 1 divided by 2 power K. All right. Now repeat this experiment n times. Repeat this experiment n times. And that means you are tossing the coin how many times? So there are nk tosses, but you don't care about that. Just repeat this experiment n times. Then the P of S complement, blah, 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 S complement n times. This is equal to 2 power K minus 1 by 2 power K whole power n. So limit n going to infinity of P of this above event, which is equal to limit n going to infinity 2 power K minus 1 divided by 2 power K, which is of course 0. Whole power n, sorry. K is fixed, okay? It's the n which is varying. Therefore, you may conclude, therefore, S has to occur eventually. Okay, I wanted to do some more, but I ran out of time. Yeah, the next class is on following Monday, Wednesday being a holiday. Okay, all right. So let me stop sharing. And yeah, let me end my lecture here.